Traveller, you arrived here for a reason. Perhaps the cosmos nudged you gently, deliberately toward a question whispered between the stars. What are the odds that an object the size of Manhattan drifts through our system and doesn't flinch when a solar storm strikes it with the force of millions of nuclear bombs? Scientists call it through Atlas, a fragment of another star, a silent visitor, threading a 1 in 20,000 path between Mars and the Sun. A whisper hidden in plasma and light. What if its calm is the real message? What if resilience is the signal we were meant to notice? Stay a while, traveller. The closer we look at 3 Atlas, the more the universe seems to remind us that certainty is a luxury we have not yet earned. 12 miles from the passing object, a camera aboard a Martian orbiter captured photons that should have answered our questions with comforting clarity. At that range, surface morphology should have resolved into gradients of reflectance. Jet sources should have revealed themselves as discrete outgassing loci, and compositional variations should have appeared as subtle shifts in albedo. Yet the images remain unseen, not because they are corrupted or trivial, but because what they contain does not align with any canonical model of cometary physics. Silence in this case is not absence but hesitation, the pause in science when data contradicts the framework built to interpret it. Researchers who briefly accessed the Mars flyby images described them with careful, deliberate ambiguity. The phrase could reveal recurs in their notes, a conditional tense that in scientific discourse rarely implies uncertainty. Rather, it implies the opposite, that analysis is ongoing precisely because something in the raw light pattern demands explanation. The scientific method tolerates anomalies, but it does not rush to publicise them. For now, the photographs rest within institutional review, suspended between revelation and restraint. In the meantime, we return to the observations we can speak about openly. On August 14th, 2025, the Very Large Telescope in Chile locked onto 3I Atlas, when it was nearly 4 astronomical units from the Sun, a region where cometary nuclei should remain inert, their volatiles, trapped beneath cryogenic temperatures. But the spectrograph recorded an emission line no model predicted: neutral nickel vapour radiating in a thin luminous envelope around the object. At such distances, equilibrium temperatures hover near 100 Kelvin. The phase transition required to sublimate nickel demands energies on the order of 2,900 Eurokilowatts. The gap is not marginal, it is a thermodynamic gulf. Rohatgalnkar and Seligman, the observers who analysed the spectrum, suggested that exotic carbonyl complexes might be dissociating under solar ultraviolet flux, releasing nickel in metastable states. It is an elegant hypothesis, mathematically defensible, chemically unconventional. Yet the underlying difficulty remains. These complexes have never been observed, never isolated, never modelled in natural astrophysical environments. A solution that explains one anomaly by invoking another is not a resolution. It is a placeholder. More troubling still is the absence of iron in the spectroscopic signature. Nickel and iron are bonded companions across cosmochemistry. They co-condense in primordial nebulae, coexist in metallic cores, co-vaporize in meteoroids, entering planetary atmospheres. For nickel to appear without iron is as improbable as detecting ionized hydrogen without accompanying helium. It violates the elemental ratios expected from stellar nuclear synthesis. To vaporize nickel in isolation is not simply unusual, it challenges the thermochemical heritage of the material itself. When the James Webb Space Telescope examined 3I Atlas, it provided a second fracture point in our understanding. Rather than confirming a water-dominated coma consistent with typical icy bodies, JWST detected a volatile inventory. Inverted in composition, carbon dioxide was dominant with water, present only as a secondary component. In solar system comets, water ice is often responsible for 80–90% of the outgassing profile. The reversed ratio implies an origin in a region colder than anything known in our Kuiper Belt or Oort cloud, a zone where CO2 condenses readily, where water remains rigidly locked, where starlight fails to impart enough thermal energy to lift molecules into space. The implication is not metaphorical, it is chronological. Such a comet would have formed billions of years ago in a circumstellar disk far more frigid than our own. It might predate the Sun. It might carry isotopic memories of a molecular cloud that has long since dispersed into the galactic background. To study it is to study the relic chemistry of a system we may never locate on a star map, and yet this relic behaves nothing like a fossil. It is excessively active at distances where activity should be negligible. It expelled water vapour at 3 astronomical units. It released nickel vapour at 4. It brightened before solar heating should have penetrated even the shallowest layers of its nucleus. Dormancy would have been expected. Instead, we observed dynamism. Then came the anti-tail, a structure projecting sunward rather than away from the sun, contradicting the radiant pressure mechanics that govern dust ejection. Anti-tails can occur through optical alignment when Earth crosses a comet's orbital plane, reprojecting older dust into a forward-facing configuration. But here the geometry did not remain static. The feature appeared intensified and rotated, eventually transitioning into a conventional dust tail, aligned with solar radiation. Rotation alone cannot easily account for such behaviour. Outgassing anisotropy can produce torque, but the coherence of the transformation suggests an emission pattern more structured than stochastic sublimation. Dr. Avi Loeb proposed that the observed evolution resembled controlled manoeuvring not as a definitive conclusion, but as a hypothesis that could not be excluded. Even critics conceded that each anomaly was explainable in isolation, yet together they accumulated into a statistical burden. As the comet prepares for its passage behind the Sun, we enter a period of forced ignorance. The inner solar glare will render it unobservable. Instruments across Earth's surface will fall silent not by choice, but by geometry. Only after perihelion, when it emerges into the dawn sky in early November, will we learn whether its brightness evolved, whether its trajectory shifted, whether any stress fractures propagated through the nucleus. The delay is unavoidable. Science, like the cosmos, often asks us to wait. In this intermission, 3I Atlas becomes not only an object of study, but a reminder of epistemic humility. Data does not arrive on our schedule. The universe does not reveal itself in linear chapters. Some phenomena resist immediate classification not to elude us, but to require patience, a quality increasingly rare in an age that demands instant resolution. Tonight the anomaly continues its orbit indifferent to our questions, and we continue our vigil shaping hypotheses from fragments of light. It is all right not to understand. The cosmos will keep its silence a little longer. As the unresolved questions accumulate around 3I Atlas, the scientific community confronts an increasingly complex puzzle, one that refuses to conform to either familiar cometary mechanics or simple anomaly dismissal. If Part 1 dealt with the unease surrounding missing images and unexpected chemical signatures, Part 2 turns toward the deeper structural and dynamical contradictions, the questions about how an interstellar nucleus can behave with such coherence in an environment designed to test the limits of matter itself. The nickel emission, a spectroscopic outlier, was only the first fracture line in the standard model. Its counterpart, the absence of iron, forces a re-examination of material origins. Elemental ratios emerge from well-understood stellar processes and early nebula condensation sequences. They do not spontaneously decouple after billions of years. A nucleus releasing nickel without iron suggests either a primordial compositional asymmetry or a selective exposure mechanism that strips away one metal while preserving another. Neither fits comfortably within known cosmochemical pathways. In astrophysics, asymmetry demands cause and cause demands history, yet the object's history is written in a language we do not yet decipher. The next anomaly resides not in chemistry but in behaviour. At heliocentric distances where sublimation pressures should be negligible, 3I Atlas persists in releasing volatiles with a magnitude and persistence inconsistent with thermal equilibrium. Models of sublimation rely on enthalpy thresholds. Surface ices require specific energy inputs before volatilization can occur. Yet this nucleus, ancient and presumably thermally insulated, activates prematurely. Water sublimation at 3 astronomical units could be rationalized as early insulation of shallow deposits, but nickel vapor at 4 astronomical units cannot. Any physical mechanism invoked to explain the activity fracturing amorphous, To crystalline phase transitions, volatile pockets must also explain why such processes initiate at temperatures far below their theoretical activation points. The appearance of the anti-tail complicates the picture further. Dust dynamics around comets follow predictable interactions between solar radiation pressure, gravitational gradients, and particle size distributions. Anti-tails, when they appear, do so through optical alignment. The perspective from Earth occasionally reprojects previously emitted dust into a sunward line of sight. Yet with 3i Atlas, the anti-tail evolves in real time. It grows, intensifies, rotates and transitions into a conventional tail, with a coherence that surpasses random particulate dispersion. The underlying pattern suggests a controlled redistribution of material, not controlled in the technological sense, but in the physical sense of being governed by internal structure rather than surface chaos. This raises the question of nucleus integrity. Cometary nuclei are typically conglomerates of dust and ice, porous and fragile, with compressive strengths comparable to loosely packed snow. They fracture under tidal forces, thermal stresses, and rotational acceleration. Yet the dynamical behaviour of 3i Atlas implies a nucleus capable of maintaining stability under conditions that routinely destabilise similar bodies. For a structure estimated between 2 and 6 kilometres across, the ability to preserve rotational coherence, sustain anisotropic outgassing, and maintain geometric predictability suggests a rigidity inconsistent with aggregate ice. The nucleus may possess a denser internal matrix, a lithified architecture formed under pressure regimes different from those of the solar nebula. When planetary scientists examine high-activity comets, they often find clues to internal heterogeneity, layered terrains, stratified materials or embedded mineral phases that influence outgassing behaviour. If 3i Atlas contains metallic inclusions that become exposed through erosion, the vaporization of surface nickel becomes conceivable, even if still thermodynamically difficult. Iron-poor metallic domains might originate from differentiated bodies or collision fragments, though such origins imply a parent environment more dynamic than a quiet protoplanetary disk. Whether that environment lies within a surviving stellar system or within one that has long since dissolved into the galactic continuum remains unknown. The structural anomaly connects directly to the dynamical one, the comet's trajectory. Hyperbolic objects entering the solar system typically exhibit small but measurable non-gravitational accelerations from outgassing asymmetry. Their orbits adjust subtly as jets impart microthrust. Yet observations of 3i Atlas show a near-perfect adherence to predicted trajectories even after solar wind events that should alter motion through momentum transfer. This suggests that either outgassing is balanced with exceptional precision, or the nucleus's mass distribution dampens perturbations to an extent beyond expectation. In either case, gravitational modelling faces a challenge. The object behaves as if its inertia buffer is far larger than its estimated mass would suggest. The quiet implication is that mass estimates may be wrong. Photometric brightness does not scale linearly with size. Albedo assumptions introduce significant uncertainty. A compact metal-rich nucleus could mimic the luminosity profile of a larger ice-dominant one. Alternatively, a highly cohesive structure could resist fragmentation and rotational acceleration in ways that give the appearance of high mass without requiring it. Either scenario would force revision of the statistical models predicting how interstellar debris is distributed across size classes in the galaxy. These scientific tensions accumulate without tipping into crisis, because astronomy by nature tolerates ambiguity. Observations often precede theory, data often outpaces explanation. Yet the recurring theme across each anomaly is not contradiction but incompleteness. The frameworks built to describe cometary behaviour function well within our solar system, but 3i Atlas originates elsewhere. It carries with it the chemical and dynamical heritage of a system not governed by our assumptions, not shaped by our sun, not constrained by the evolutionary pressures that formed our comets. The farther we trace the implications, the more we confront an epistemological boundary. Our models are not incorrect. They are local. They describe the subset of cosmic behaviour we have witnessed. 3is Atlas expands that domain by introducing phenomena that, while unfamiliar, may be entirely ordinary within its system of origin. In this sense, The anomalies are not violations, but signals evidence that the cosmos exhibits a diversity of formation environments far broader than our brief observational history has sampled. As the comet moves behind the Sun, the scientific community waits not for resolution but for refinement. The unanswered questions will not vanish, they will sharpen. Observations after perihelion may alter trajectories, brightness curves or spectral signatures. They may confirm existing concerns or dissolve them into ordinary explanation. What matters is not which outcome arrives, but that each data point expands the perimeter of what we know. In the end, Three-Eye Atlas is not an anomaly to be solved, but a reminder that scientific understanding evolves through contact with the unfamiliar. Our instruments record light, our theories interpret it, but the universe itself remains under no obligation to conform to our expectations. We observe, we analyse, and we learn always with the awareness that the next visitor may arrive with an entirely different vocabulary of phenomena. As the trajectory of Three-Eye Atlas carries it farther through the inner solar system, the object forces a deeper reconsideration of the dynamical assumptions that govern our understanding of interstellar wanderers. Hyperbolic bodies usually reveal their presence through small but measurable deviations from gravitational predictions, subtle drifts caused by asymmetric outgassing or surface fragmentation. Yet this object continues to trace its projected orbit, with a precision that seems almost engineered. Its stability challenges decades of cometary mechanics, suggesting either an unusually high nucleus cohesion or a volatile release pattern so symmetric that net acceleration is effectively nullified. Both interpretations require physical properties not commonly associated with fragile porous aggregates of ice and dust. The structural question cannot be separated from the compositional one. A nucleus with appreciable metallic content or consolidated mineral phases would exhibit greater resistance to perturbation, but for such resistance to persist through billions of years of cosmic radiation, micro-impacts and thermal cycling, the material must have formed under pressure or temperature regimes different from any observed in the outer solar nebula. This implies a birth environment whose thermodynamic profiles diverged significantly from those surrounding our own Sun. The unusual CO2 to H2O ratio already points toward a colder formation zone, perhaps near the distant periphery of a protoplanetary disk or within a region shielded from stellar radiation by dense molecular clouds. Such environments preserve volatiles with higher sublimation thresholds and prevent early differentiation, allowing chemical architectures to remain frozen across cosmic time. Thermal behaviour provides another window into this alien origin. Comets awaken as solar radiation penetrates their surfaces, but activation thresholds vary with ice composition, porosity and conductive pathways. Atlas displays thermal activation well beyond established distances, suggesting either deep-seated volatiles exposed through structural channels or a nucleus whose physical arrangement enhances internal heat transfer. If conductive minerals are embedded within the matrix, they could redistribute absorbed energy-warming subsurface layers while leaving the exterior deceptively cold. Such dynamics would enable early outgassing consistent with both the water release at 3 astronomical units and the nickel vapour detected near 4. The latter remains the most enigmatic feature, requiring temperatures that cannot be explained by solar heating alone. Vaporization of nickel implies localized hotspots, perhaps associated with metallic inclusions exposed through fracturing or erosion. In that case, iron-poor nickel-rich zones would need to exist in isolation, an arrangement rarely seen in natural planetary materials unless shaped by atypical processes. The plasma interaction with the Sun underscores the object's resilience. Coronal mass ejections emit charged particles that can erode cometary surfaces, alter rotation rates, and in severe cases fragment nuclei entirely. The lack of measurable alteration in Atlas after such an event suggests surface cohesion orders of magnitude stronger than the typical tensile strength of icy aggregates. Electrostatic stress, mechanical loading, and ion ablation should have induced observable changes, yet the coma reformed steadily, and the predicted orbit held. The absence of fragmentation points toward an internal rigidity incompatible with loosely bound grains. If crystalline phases or sintered materials dominate the structure, they may provide the necessary resilience. Conversely, the nucleus may contain a layering architecture, where low-density material is shielded beneath denser strata, allowing the exterior to withstand plasma pressures without catastrophic failure. Ion tail behaviour during the CME also offers insight. Under normal conditions, ion tails realign with magnetic field lines in predictable patterns, but their response time depends on ionization efficiency and dust loading. The rapid stabilization of Atlas's tail indicates a coma dominated by molecules with high ionization cross-sections, consistent with CO2-rich chemistry. This would also explain the temporary weakening of optical signals, as the plasma environment may have accelerated ion stripping and reduced photon emission events in the near-nucleus region. The weak signal described by observers is therefore not evidence of inactivity, but rather a consequence of plasma-induced suppression of visible emissions. The question of how such an object arrives in the solar system cannot be addressed without considering galactic-scale dynamics. Interstellar objects are produced in staggering numbers through gravitational scattering during planetary formation, stellar flybys and disk instabilities. Over billions of years, these bodies disperse throughout the galaxy, populating interstellar space with a background flux of debris. Most drift unseen. Only those intersecting the narrow observational cone of Earth-based surveys are detected. Atlas is significant not because it is unique, but because modern survey instruments have finally reached the sensitivity necessary to detect such visitors. Its trajectory passing close to multiple planets appears unusually convenient, yet this too may be a product of observational bias. We notice only the objects that pass near enough to provoke interest. Still, its precise path raises questions about early perturbations that shaped its final approach. Gravitational interactions with massive bodies in its home system could have imparted the velocity necessary for ejection, while random stellar encounters may have redirected its course over vast timescales. The result is a trajectory that, while improbable on human timescales, becomes inevitable on cosmic ones. The solar system is merely the latest waypoint in a journey measured not in millions, but in billions of years. Each anomaly associated with Atlas, its unusual chemistry, unexpected activity, structural coherence and dynamical precision, may ultimately reflect nothing more than the incompleteness of our local frameworks. Scientific models are built upon limited data derived from a single system, our own. Interstellar bodies provide the first direct samples of cosmochemical diversity beyond that narrow context. What appears anomalous may simply be typical for comets, formed under different stellar metallicities, radiation regimes, or disk compositions. The role of Atlas, then, is not to overturn our understanding, but to expand its boundaries. It forces reconsideration of sublimation thermodynamics, plasma interactions, compositional evolution, and the structural diversity of small bodies. More importantly, it highlights the need for theoretical models capable of accommodating chemical and physical behaviours that fall outside the expectations set by solar system objects. The deeper significance of this interstellar wanderer lies not in any singular anomaly, but in the recognition that the cosmos contains a spectrum of formation environments far broader than our prior observational records implied. As more such visitors are detected, the scientific community will be compelled to revise long-standing assumptions about planetary formation, volatile chemistry, and the architectures of small bodies. Atlas is not an exception. It is the beginning of a data set, and through it we are reminded that the universe is larger not only in scale but in possibility. As observational campaigns prepare for the reappearance of Thruai Atlas, after solar conjunction attention increasingly turns toward the broader scientific implications of studying such an object. Interstellar visitors are not merely curiosities, they are empirical test cases for the limits of planetary science, astrophysics, and cosmochemistry. Each one challenges the assumptions built from a dataset restricted almost entirely to bodies formed under a single stellar regime, our suns. Atlas, by virtue of its chemical, thermal, and dynamical deviations, highlights how narrow that dataset truly is. The significance of this object lies not in its anomalies, but in its ability to widen the frame through which we interpret small body physics. One of the most consequential threads emerging from Atlas's behaviour concerns the temperature-dependent volatility of its constituent materials. In our solar system, the sublimation thresholds of water carbon dioxide, carbon monoxide, and organics determine the spatial distribution of cometary activity. These thresholds underpin models ranging from thermal evolution to coma formation and dust-gas coupling. ATLAS disrupts these assumptions by remaining active at heliocentric distances, where insulation flux is insufficient to trigger large-scale sublimation for conventional compositions. This suggests either the presence of volatiles with lower activation energies, or a nucleus capable of enhanced thermal absorption and redistribution. The CO2-dominant chemistry hints at a cold formation environment, but the early onset of activity hints at a physical structure with either higher conductive efficiency or a fracturing pattern that exposes subsurface volatiles unusually early. Understanding such behaviour will require a revision of sublimation models to incorporate parameters relevant to exosolar icy bodies. Another important consideration is the effect of solar radiation on surface evolution. As ATLAS approaches perihelion, differential heating can generate thermal stresses capable of crack propagation, rotational acceleration, and mantle disruption. Most long-period comets exhibit observable changes in morphology near perihelion, including shedding of surface layers and fragmentation of weakly cohesive structures. Yet ATLAS, despite experiencing both standard insolation and a major coronal mass ejection, displays no catastrophic response. Its coma morphology evolves, but the nucleus remains dynamically stable. This suggests a mechanical resilience reminiscent of lithified or sintered materials rather than loosely bonded ice dust aggregates. If such cohesive structures are common among interstellar comets, it would imply either a formation environment with stronger pressure gradients or a surface history shaped by processes absent in our system. The nucleus's resistance to fragmentation becomes even more intriguing when evaluated alongside its interaction with the solar wind. Charged particle flux from the Sun typically sculpts ion tails and induces photodissociation in volatile molecules. During CME encounters, the magnetohydrodynamic environment surrounding a comet becomes turbulent, dramatically altering the behaviour of ions and dust. ATLAS, however, appears to recover rapidly from such disturbances, with its ion tail establishing alignment according to the prevailing interplanetary magnetic field. This rapid recovery implies a coma environment dominated by volatiles capable of swift reionization consistent with CO2-rich chemistry. The weak signal detected after the CME may thus reflect temporary suppression of scattering processes rather than a decline in physical activity. Such observations refine our understanding of how different molecular species respond to plasma environments, particularly those not commonly observed in our solar system's comets. The dynamical trajectory of ATLAS also encourages broader inquiry. Hyperbolic objects exhibit distinctive orbital signatures that distinguish them from gravitationally bound bodies. Their velocities exceed the escape velocity of the Sun, confirming interstellar origin, yet the inbound vectors of such objects can reveal information about their dynamical histories. ATLAS's approach vector does not align with any known stellar association or moving group, suggesting ejection from a random region of the galactic disk rather than a specific origin system. Over millions of years, gravitational perturbations from stars, molecular clouds, and galactic tides can deflect an interstellar object's trajectory, erasing direct information about its birthplace. However, chemical signatures preserved in ices and refractory materials may still encode information about stellar metallicity, local radiation fields, and early disk temperatures. This makes ATLAS more than an observational target. It is a physical archive. A parallel line of investigation concerns the frequency of such archives. The discovery of multiple interstellar objects within a single decade implies that the galaxy contains a vast abundance of these bodies, far exceeding early estimates. Survey telescopes such as Pan-STARRS and ATLAS itself have improved sensitivity and cadence, revealing a population that was always present but previously invisible. Future facilities, especially the Vera C. Rubin Observatory, will likely detect many more. As the sample size grows, statistical patterns will emerge, distributions of composition, size, density, activity, and dynamical behaviour. With enough data, astrophysicists may eventually classify interstellar object populations in the same way that we classify asteroids and comets within our own system. The anomalies of ATLAS then may someday be seen not as deviations, but as signatures of a particular formation lineage. The question of how to physically study such objects also gains urgency. While telescopic observations reveal composition and dynamics, they cannot directly sample isotopic ratios or microstructural features. To truly understand an interstellar object, a spacecraft encounter is required, yet the observational window for such missions is narrow. By the time an object is detected, it is often already inbound at high velocity, and mission planning timescales exceed feasible launch windows. This has led to proposals for standby interceptors spacecraft held in reserve at strategic locations capable of rapid deployment when a suitable target is identified. Such missions would sample coma gases, analyze dust grains, and obtain high-resolution imaging of the nucleus. Even a flyby would revolutionize exosolar small-body science. Atlas, however, is not such a mission candidate. Its discovery occurred too late for interception, and its outbound trajectory will soon remove it from observational reach. For now, the object remains accessible only through electromagnetic signatures and dynamical modelling. Yet its scientific impact will endure, shaping the design of future instrumentation survey strategies and mission architectures. Perhaps the most profound implication of Atlas lies not in its anomalies, but in what it represents for planetary science. The field is transitioning from studying a single planetary system to studying many. Interstellar objects provide direct access to the building blocks of distant stars, bypassing the limitations of spectroscopy and remote sensing. They are physical messengers carrying material from environments we may never observe in situ. Through them, our understanding of planetary formation expands from a single template to a galactic spectrum. The appearance of Atlas reminds us that scientific certainty is provisional. Every data set is incomplete, every model awaits revision, and every unexplained feature is an invitation to broaden the limits of explanation. As it continues its path outward, leaving behind only a trail of ionized gas and archived measurements, the object demonstrates that ignorance is not a void, but a frontier one that widens with every new interstellar arrival. As astronomers prepare for the post-conjunction observation window, attention shifts toward the implications of Atlas's upcoming trajectory through regions dominated by the gravitational fields of Jupiter, Venus, and Mars. Each planetary encounter offers not only an opportunity for refined orbital measurements, but also a chance to evaluate how interstellar bodies respond to tidal forces within a multi-planet system. In typical long-period comets originating from the Oort cloud, close planetary approaches often lead to measurable perturbations, especially when the objects possess high angular momentum and fragile internal structures. Yet Atlas's prior behaviour suggests a nucleus capable of resisting structural deformation, even in dynamically complex environments. This creates an expectation that its future encounters will yield data of unusual clarity, unmarred by stochastic fragmentation or chaotic outgassing events. Such planetary interactions also matter because they reveal how interstellar objects integrate, however briefly, into the gravitational architecture of a foreign system. The solar system acts not merely as a waypoint, but as a diagnostic field, probing the resilience and composition of bodies forged elsewhere. If Atlas maintains trajectory coherence through multiple gravitational encounters, it may indicate an unexpectedly high material density, or a nucleus whose internal mass distribution reduces susceptibility to tidal torques. Alternatively, it may simply reflect the statistical improbability of its precise approach geometry, a reminder that cosmic events often present themselves through a mix of determinism and chance. Regardless, the encounter data will refine the gravitational models used to understand both natural visitors and hypothetical artificial probes. The absence of fragmentation thus far remains one of Atlas's central mysteries. Comets approaching perihelion often experience rotational acceleration as anisotropic outgassing creates torque-altering spin states and inducing centrifugal stress. If rotation periods shorten beyond structural tolerance, the nucleus can undergo mass-shedding fissuring or complete breakup. Observations of objects such as Comet 41P or 332P illustrate this vulnerability vividly. Atlas, however, shows no sign of such rotational instability. Its coma expansion occurs without detectable shifts in the rotational period, implying that either its jets produce minimal torque or its nucleus possesses internal cohesion far greater than expected for an icy body. The persistence of stable rotation under increasing thermal stress may point toward an internal framework, reinforced by mineral phases or mechanically interlocked structures rather than granular aggregates. Thermal inertia also plays a significant role in determining how cometary surfaces evolve with increasing solar proximity. Materials with high thermal inertia respond slowly to temperature changes, reducing the amplitude of diurnal cycles and limiting the formation of large-scale fractures. If Atlas exhibits unusually high thermal inertia, it would experience less thermal fatigue and thus fewer structural disruptions. Such behaviour would be consistent with a nucleus containing densely sintered ice-low porosity or conductive inclusions that distribute absorbed energy throughout the object. In this sense, Atlas's resilience may reflect not anomalous strength, but simply the consequences of a formation environment that favoured compaction and mineralisation. The interstellar context in which it formed may have lacked the high energy collisions that introduce heterogeneity into many solar system comets. Beyond structural resilience, the chemical composition of Atlas continues to reshape theoretical expectations. The dominance of CO2 over H2O in its coma complicates existing sublimation models as carbon dioxide transitions to gas at much lower temperatures than water. This creates a scenario in which CO2-driven jets may activate long before solar radiation becomes sufficient to liberate water vapour. If these jets originate from well-distributed subsurface reservoirs, they may generate a form of self-stabilising outgassing one, in which momentum changes cancel out over time, preserving orbital predictability. In this way, the chemical anomaly may be directly responsible for the dynamical precision that initially seemed so puzzling. The detection of carbon monoxide and cyanogen adds nuance to this picture. Both molecules are associated with extremely cold formation environments, and often exist only in deeply buried layers of solar system comets. Their early and consistent release in Atlas suggests that the object has undergone minimal thermal processing during its interstellar migration. This allows it to serve as an effectively pristine sample of exosolar chemistry. For cosmochemists, such an object is invaluable, a direct physical representative of a molecular cloud fragment, frozen since the earliest epochs of its parent system. The isotopic ratios within these volatiles, if they could be measured directly, would offer unprecedented insight into nucleosynthetic processes beyond our Sun's local environment. The evolution of Atlas's dust tail adds yet another layer of complexity. Dust dynamics depend on particle size distribution, emission velocity, and the balance between radiation pressure and gravitational attraction. The antitail phenomenon observed earlier, while potentially attributable to geometric projection effects, displayed a temporal evolution too structured to dismiss outright. Its growth, rotation, and eventual transformation into a standard dust tail imply a time-dependent emission pattern that may reflect internal reorganization of volatile layers or selective activation of localized jets. Understanding this behavior requires integrating photometric data dust scattering models and three-dimensional dynamical simulations. If similar patterns appear in future interstellar visitors, it may signal a distinct class of dust layering or volatile stratification not represented in solar system comet populations. As observational teams prepare for renewed study, the importance of coordinated global efforts becomes apparent. Planetary defense networks such as the International Asteroid Warning Network rely on precisely these observational campaigns to refine tracking methodologies. Interstellar objects with their high velocities and unpredictable composition serve as ideal calibration tools. Atlas's upcoming visibility window will allow for astrometric measurements of unprecedented accuracy, thanks to distributed observations across different latitudes and longitudes. These measurements will inform not only models of orbital evolution, but also strategies for tracking objects that may one day pose a threat to Earth. In this sense, Atlas participates in a form of indirect planetary protection, teaching the scientific community how to interpret complex coma interference motion biases and radiation pressure anomalies. The need for adaptable models extends beyond defense. The increasing detection of interstellar objects heralds a new frontier in planetary science, one that demands theories capable of accommodating diverse chemical and physical behaviors. Each visitor expands the parameter space, compelling revisions to assumptions about formation temperatures, disk metallicities, and thermal evolution. Atlas's deviations from normative expectations highlight how rarely our models have been tested against exosolar data. As more such objects arrive, patterns will emerge revealing the structural families and compositional signatures of distant stellar nurseries. In time, the galaxy's small body population may prove as diverse as its stars, each fragment bearing the imprint of a unique thermodynamic history. The scientific community stands at the threshold of a paradigm shift. For the first time, the building blocks of distant systems are arriving on empirical terms, not as photons in a spectrum, but as tangible, measurable matter passing through local space. Atlas exemplifies this transition. Its chemical anomalies, dynamical precision, and structural resilience are not curiosities. They are early indicators that the physics of exosolar small bodies may differ meaningfully from those of our own. In studying such objects, we widen our understanding of planetary formation chemical evolution and the diversity of worlds beyond our reach. As 3i Atlas moves toward the post-conjunction observational window, the scientific community turns increasingly toward the unresolved question of what this object represents in the broader taxonomy of interstellar debris. Its behaviour suggests a category not fully encompassed by our current cometry definitions, an object whose physical, chemical, and dynamical attributes deviate from the archetypes shaped by our solar system's history. The challenge now is not simply to catalogue anomalies, but to determine whether these deviations reflect unique circumstances or a class of objects yet to be defined. One emerging perspective views Atlas as a transitional body, bridging the conceptual gap between volatile-rich comets and structurally consolidated minor planets. Its early activation, sustained activity, and mechanical integrity suggest a nucleus that incorporates both ancient ices and refractory materials arranged in a configuration unfamiliar to classical comet physics. If this interpretation is correct, then Atlas may not be an outlier, but the first example of an interstellar hybrid small body forged in an environment with thermal gradients, dust loads, and pressure regimes different from any region previously modelled. In attempting to contextualize this object, researchers increasingly turn to the discipline of comparative planetology, drawing analogies between exosolar formation environments and the chemical structures preserved in Atlas's emitted volatiles. Molecular ratios represent the fossil signatures of a long-vanished disk, retaining information about ambient radiation levels, local density fluctuations, and the chronology of planetary assembly. For instance, the CO2 predominance suggests formation outside the traditional water snowline, perhaps near the outer boundaries of a protoplanetary disk, where temperature gradients flatten and CO-rich ices accumulate. The presence of cyanogen further supports an origin in a cold nitrogen-rich region, minimally processed by stellar irradiation. Such signatures are rare in solar system comets, implying that Atlas's birthplace may have been a quiescent or slowly evolving disk, not unlike the colder, less turbulent environments hypothesized around low-mass stars. Over billions of years, gravitational encounters would have altered its trajectory, but its molecular composition remains a more reliable indicator of its ancestral conditions than any dynamical model. However, composition alone does not explain Atlas's anomalous structural behaviour. The absence of fragmentation under thermal stress and plasma exposure suggests internal cohesion significantly greater than typical cometary tensile strength. This raises the possibility that the nucleus contains not only frozen volatiles, but also lithified or partially crystalline phases. In planetary materials, cohesion arises from sintering pressure, induced compaction or chemical bonding at grain boundaries. If Atlas formed in a region where dust-grain collisions occurred at velocities conducive to compaction, rather than fragmentation, or if its materials experienced episodic heating before ejection, then the result would be a nucleus with a comparatively rigid internal matrix. Such a structure would resist tidal distortion, maintain rotational stability, and suppress catastrophic mass loss even during intense solar encounters. This hypothesis aligns with observations from certain trans-Neptunian objects, which exhibit unexpectedly high densities and mechanical strengths inconsistent with loosely aggregated ice. Atlas may belong to this category, but translated into an interstellar context. The dust environment surrounding Atlas offers additional clues. Its anti-tail behaviour, while initially interpretable through geometric projection effects, exhibits temporal evolution suggestive of structured dust release. The sequence are rapid formation, strengthening rotational transformation, and subsequent transition into a conventional dust tail requires dust particle ejection with evolving velocity vectors. These vectors must correlate with changes in localized sublimation fronts, or the exposure of deeper volatile pockets. Numerical modeling indicates that such behavior could result from rotational modulation of CO2-driven jets interacting with dust layers of varying grain sizes. Fine grains respond strongly to solar radiation pressure, while larger grains remain gravitationally constrained. The rotating dust features may thus reflect a stratified nucleus, where different layers sublimate at different heliocentric distances. If such stratification is common among interstellar bodies, it would imply a formation or evolutionary history involving episodic accretion or layer deposition within their parent system. Attention now turns toward the orbital mechanics of the object's future path. As Atlas approaches regions influenced by Jupiter's gravitational field, its trajectory will provide critical data on how interstellar bodies respond to complex N-body interactions within a planetary system. Even if the comet's structural integrity remains constant, subtle gravitational perturbations will allow researchers to refine its inbound velocity vector and estimate its pre-solar trajectory more accurately. While such reconstructions rarely identify a specific parent star owing to billions of years of galactic dynamical diffusion, they can constrain the object's likely stellar environment, ruling out high-velocity populations or dynamically hot regions such as the galactic thick disk. The refined trajectory may also help assess whether Atlas experienced close stellar encounters before reaching the solar system encounters that may have exposed or altered its surface layers. As interstellar science advances, Atlas's role becomes increasingly pedagogical. It demonstrates the necessity of modular models capable of integrating behaviors that fall outside traditional cometry frameworks. The object's dynamical stability challenges assumptions about non-gravitational forces, its volatile profile challenges sublimation models, and its mechanical resilience challenges expectations derived from low-density cometry nuclei. Each challenge is not a contradiction, but an opportunity to refine our models in a direction more consistent with exosolar diversity. In this sense, Atlas is less a mystery and more a calibration point, one that forces planetary scientists to consider that our solar system represents only one permutation of small body formation chemistry and evolution. Equally important is the recognition that Atlas serves as a precursor to a burgeoning field. The Vera C. Rubin Observatory's forthcoming survey capabilities will dramatically increase the detection rate of interstellar objects, enabling comparative studies across a statistically meaningful sample. With each new detection, the contextual framework built around Atlas will either expand or sharpen, revealing whether its anomalies are characteristic of a broader population or idiosyncratic to its formation environment. Should additional interstellar comets exhibit similar CO2 dominance dust structures or dynamical precision, a new classification scheme may become necessary, one that explicitly distinguishes between solar analog formations and exosolar chemistries. Ultimately, Atlas exemplifies the transition from observational astronomy to a more integrative exosolar materials science. It represents not only a single interstellar fragment, but a conceptual bridge toward understanding the chemical and structural diversity of small bodies beyond our Sun. As it continues outbound after perihelion, its fading signal becomes less a loss than an invitation, a prompt to refine our theories, adjust our expectations, and prepare for the next messenger forged under distant stars. As 3 Atlas recedes from the Sun's immediate domain, its trajectory through the inner solar system becomes a dynamic laboratory for studying the interaction between interstellar materials and heliophysical forces. Each incremental change in brightness coma geometry or dust morphology acts as a diagnostic signal, revealing the microphysics governing its surface and subsurface processes. The heliocentric distance now increases, reducing the instant solar fleets, yet Atlas maintains a level of outgassing that defies thermal equilibrium predictions for CO2 and CO-dominated nuclei. This persistence implies either the presence of deeper volatile reservoirs insulated by low conductivity materials, or a mechanism whereby gas migrates through microfractures established earlier during perihelion heating. the comet's thermal inertia becomes central to these interpretations. A nucleus composed of layered, partially sintered grains with varying porosity would retain thermal gradients long after perihelion, sustaining sublimation from interior strata even as the surface cools. Such thermal lag is consistent with observations of certain long-period comets, though never at this magnitude or with such a prolonged emission profile. Thus, Atlas continues to rewrite the parameters of what sublimation can achieve when the nucleus originates under conditions unlike any represented in the solar system. The dust environment remains equally instructive. As solar radiation pressure reasserts dominance in the post-perihelion phase, dust grain trajectories diverge according to grain mass composition and charge state. The plasma interactions experienced near perihelion likely altered grain charging embedding surface potentials into ejected dust that now respond asymmetrically to electromagnetic fields. Studies of dust plasma coupling in cometary atmospheres suggest that even minor surface charge heterogeneities propagate into observable tail distortions at macroscopic scales. Atlas's earlier anti-tail evolution may thus replay in reverse, not as a rotation-driven effect but as charge diffusion interacts with the solar wind's declining density. If this occurs, researchers expect to see faint curvilinear dust structures diverging from the primary tail axis structures that could serve as tracers for particle charge decay rates, providing rare empirical constraints for plasma-comet interaction models. The significance lies in the fact that Atlas has already demonstrated dust behaviours unaccounted for in current frameworks, suggesting that each additional dataset contributes to a slow but necessary expansion of cometary plasma physics. The gas coma offers another domain of active study. Spectroscopic monitoring post-perihelion allows researchers to quantify the temporal evolution of volatile abundance ratios, especially the CO2 gaseous chest H2O CO triad that defines Atlas's unique chemical signature. As heliocentric distance increases, the sublimation curve steepens favouring CO release due to its lower latent heat of sublimation compared to CO2 and H2O. If Atlas's activity remains CO2 dominated even at increasing distances, this would require either large reservoirs of CO2 ice, accessible to sublimation, or the breakdown of carbon-bearing complex ices that liberate CO2 as secondary products. Alternatively, sustained CO2 release could imply a structural architecture in which CO2-rich materials dominate near surface layers, while water ice resides deeper within the nucleus. Such stratification fits models of planetesimal formation, where radial drift and condensation gradients separate volatile species before accretion. The implication would be that Atlas preserves the radial chemistry of its birth disk, a rare survival of primordial compositional zoning. Detailed mapping of these ratios over time could reveal whether the sublimation front migrates inward uniformly or encounters compositional boundaries indicative of episodic formation. Observers also anticipate that Atlas's rotation state may evolve subtly as outgassing torques diminish unevenly across the surface. Early predictions placed its rotation period within the typical range for kilometre-scale cometary nuclei, but the lack of fragmentation and the sustained rigidity of the object suggest that the nucleus distributes stress more efficiently than porous aggregates. If the rotational period is measured to have increased or decreased post-perihelion, the torque direction and magnitude will offer clues to the internal heterogeneity of volatile pockets. A rotation acceleration, for example, could signal asymmetric sublimation from persistent warm regions, while deceleration might imply the exposure of new vents with opposing torque signatures. These parameters are difficult to isolate, but high cadence photometry from coordinated observatories during the Hatwind campaign will provide light curves capable of resolving rotational harmonics. Any deviation in the expected periodicity will refine models of internal density distribution, offering the first indirect glimpse into the object's structural anatomy. Another emerging field of inquiry concerns the sputtering processes induced by solar wind ions during the perihelion passage. The intense plasma encounter Atlas survived likely implanted solar wind ions into the nucleus's upper layers, altering the surface chemistry in ways that optical observations alone cannot detect. Laboratory analogues of ion sputtering at cryogenic temperatures show that implanted ions can destabilize molecular bonds, forming metastable radicals that later recombine or dissociate during thermal cycling. This means Atlas's surface could now contain ion-modified ices with chemical signatures that differ from its primordial state. As the comet cools, sublimation from these ion-processed regions may generate transient spectral lines, weak short-lived but detectable with sensitive instrumentation. Detecting such lines would confirm a direct chemical imprint from the CME impact, and provide the first observational evidence of how interstellar materials respond to extreme solar plasma events. This knowledge extends beyond curiosity. It informs models of space weathering on icy bodies both interstellar and solar, and may clarify how organics, volatiles, and minerals chemically evolve under repeated stellar wind exposure. Dynamical interactions remain a central theme in Atlas's post-perihelion science case. As it approaches the region influenced by Jupiter's gradient field, slight deviations in the predicted path could reveal whether non-gravitational forces, primarily outgassing recoil, still influence its motion. For most comets, the fading of activity at greater heliocentric distances corresponds to a reduction in such forces. But Atlas's anomalous early activation suggests that sublimation may remain significant at larger distances than traditionally expected. Should its trajectory reveal persistent non-gravitational acceleration, this would confirm that deep reservoirs of volatiles continue to drive measurable thrust, implying an unexpectedly permeable or channel-rich subsurface. If conversely its trajectory becomes purely gravitational, the cessation of non-gravitational effects will help determine the depth at which volatile depletion stabilizes. Both outcomes refine the broader understanding of how interstellar comets evolve dynamically as they encounter stellar environments unlike their own. Increasingly, Atlas is becoming a focal point for the emerging discipline of galactic small-body exchange. Its behavior raises questions about the survivability of icy bodies over multi-Geiger-year timescales in the interstellar medium. Exposure to cosmic rays, micrometeoroid bombardment, and the general thermal vacuum of deep space should degrade surface materials, gradually eroding volatiles and darkening refractory components. Yet Atlas's activity implies the preservation of substantial volatile content despite billions of years of exposure. This suggests either that the nucleus was shielded by an insulating mantle that prevented sublimation, or that sublimation rates in interstellar space are far lower than assumed. The former hypothesis requires a thick cohesive crust perhaps formed by sintering or pressure-induced metamorphism. The latter implies that cometary models overestimate long-term volatile loss rates in low-energy environments. Both possibilities reshape how scientists conceptualize the galactic population of icy fragments and their capacity to deliver unaltered chemical information across stellar systems. The philosophical implications also become difficult to ignore. Atlas. Though a physical object serves increasingly as a conceptual instrument, one that challenges implicit biases in how planetary science generalizes from a sample size of one. It reminds researchers that solar system comets reflect a specific evolutionary history shaped by one star's radiation profile, one system's dynamical rearrangements, and one circumstellar disk. Interstellar objects like Atlas serve as counterexamples, forcing the scientific method to evolve toward a more pluralistic understanding of planetary formation. In this way, Atlas not only carries the chemical memory of its parent star, but expands the epistemic boundaries of planetary science itself. As 3i Atlas continues its outbound drift through the solar system's diminishing light, its trajectory becomes not just a physical path, but an epistemological frontier, reminding researchers that every interstellar visitor alters the framework through which planetary formation and chemical evolution are understood. The object's slow fading highlights an essential asymmetry in observational astronomy. The more distant and quiet an object becomes, the more theoretical weight its earlier brighter signals acquire. In practice, this means that the anomalous spectral signatures detected near 4AU, the nickel emission without corresponding ion lines, grow more influential in shaping scientific models precisely because they cannot be revisited under identical conditions. Nickel's vapor phase presence continues to challenge thermal models, suggesting either localized heating mechanisms or mineral phases susceptible to low-energy photon-induced dissociation. As the heliocentric distance increases, the outgassing of such metals becomes thermodynamically implausible, indicating that the earlier observations reflect fundamental compositional traits rather than transient events. Researchers now examine whether Atlas's nucleus contains nickel-rich silicates or metallic inclusions capable of releasing nickel preferentially under ultraviolet irradiation, a process rarely considered in cometary contexts, but plausible in environments where stellar radiation differs in spectral distribution from that of the Sun. If such inclusions exist, they may represent mineralogical products of a parent disk with a distinct oxidation history, perhaps one enriched in refractory metals due to localized condensation events near a young star's magnetospheric truncation radius. As the scientific community integrates these findings, attention shifts toward the broader implications for interstellar population diversity. Before Atlas, interstellar objects were treated as statistical anomalies. Afterward, they appear increasingly as representatives of a vast unseen galactic ecology. The compositional anomalies observed in Atlas hint that the diversity of interstellar bodies could exceed current estimations derived from solar system analogues. Volatile inventories, dust grain architectures, and mineral inclusions may vary significantly from system to system, reflecting localized disk chemistry, variable stellar UV flux, and the dynamical interactions that govern planetesimal scattering. For example, the dominance of CO2 in Atlas's sublimation profile implies formation at temperatures lower than those typical for Oort cloud comets, possibly near the periphery of a massive protoplanetary disk. This CO2-rich composition mirrors certain models of disks around M-dwarf or K-dwarf stars, where stellar luminosity yields broader and colder condensation zones. If this inference is correct, Atlas may not be an exception, but a preview of the kinds of interstellar comets likely to populate the galaxy volatiles shaped by stellar demographics rather than by the specific chemical evolution of a G-type star like the Sun. From a dynamical perspective, Atlas's hyperbolic trajectory and the precision with which it retained its predicted path after the CME impact offer a rare case study in the resilience of interstellar bodies to perturbative forces. Astrodynamicists examining its orbit note that the absence of significant non-gravitational deviations post-perihelion implies either exceptionally uniform outgassing or a geometric distribution of vents that balances recoil forces. This symmetrical behaviour is nearly unprecedented among highly active comets, which typically display jitter-like fluctuations arising from anisotropic sublimation. If Atlas possesses an internal structure sufficiently homogeneous to distribute heat and outgassing evenly across its surface, this would reinforce the hypothesis that it formed in a disk environment conducive to uniform accretion, possibly involving slow coagulation of fine grains rather than hierarchical assembly of large aggregates. Such structural regularity would explain why the object survived intense solar plasma exposure without deformation. Its internal tensile strength may be closer to that of compacted cryogenic material than to the porous aggregates seen in many solar system comets. The prospect of assessing Atlas's rotation state as it cools further deepens scientific interest. Changes in light curve amplitude or periodicity could reveal whether sublimation has exposed regions of varying albedo or surface roughness. Moreover, if the rotational period shifts gradually with distance, this may indicate residual torques acting from delayed gas release stored in insulated internal pockets. These processes resemble thermal breathing mechanisms observed on certain cometary nuclei, where phase transitions of volatiles amplify or dampen rotational acceleration over time. Monitoring Atlas's rotational evolution thus becomes a window into internal processes otherwise inaccessible, potentially distinguishing between monolithic lightly cracked structures and multi-layered configurations with interlaced volatile reservoirs. In addition to its compositional and dynamical signatures, Atlas serves as a probe into the long-term survivability of icy bodies in the interstellar medium. The persistence of volatiles after billions of years raises questions about the thermal environment of interstellar space and its capacity to preserve complex ices. Traditional models assume gradual desorption driven by cosmic ray heating, yet Atlas's activity indicates that its volatile inventory remains largely intact. This may suggest that comet-sized bodies experience less radiolytic degradation than predicted, or that protective crusts formed by micrometeoroid sintering or radiation-induced polymerization shield deeper layers from cosmic ray penetration. Laboratory simulations of radiation hardening in mixed ices support the possibility of such crust formation, implying that interstellar comets could function as long-duration cryogenic capsules, preserving chemical conditions from epochs long before the Sun formed. This concept bridges astronomy with astrobiology, raising the possibility that prebiotic chemistry initiated in one stellar system may be transported intact and detectable to another across galactic distances. Moreover, Atlas's journey underscores the importance of future detection infrastructure. Instruments like the Vera-C, Rubin Observatory will soon expand the known population of interstellar objects from a handful to potentially dozens per year. This shift will allow comparative population studies where anomalies in objects like Atlas can be contextualized within a broader statistical framework. If repeated patterns such as CO2 dominant sublimation metal, rich gas emissions, or symmetric dynamical behavior may define new categories of small body evolution, shaped by galactic chemical gradients. Conversely, if Atlas remains an outlier among future detections, it will anchor the extremes of interstellar diversity rather than the norm. Either outcome deepens our understanding of the galaxy's small body inventory and the processes that launch such objects into interstellar trajectories. Finally, Atlas continues to remind researchers that observational astronomy operates at the boundary between empirical science and conceptual humility. The object embodies a paradox familiar in cosmology. Proximity reveals complexity, but distance confers perspective. While Atlas's physical details fade with each passing day, the theoretical structures built from its brief bright interval endure. It becomes a reference point for interpreting future interstellar detections, a calibration marker for volatile retention models, and a catalyst for revisiting assumptions about the chemical homogeneity of planet-forming disks. In this sense, Atlas does not recede into obscurity. It migrates into theory, into the architectures of understanding that shape how scientists conceptualize the galactic environment. Its departure marks not an ending, but an expansion of inquiry demonstrating that even a transient visitor can permanently alter the intellectual landscape of planetary science. As 3i Atlas advances outward beyond the primary influence of the inner solar system, the diminishing solar flux reveals a different phase of its evolution, one governed less by sublimative kinetics, and more by the slow relaxation of internal energy, residual molecular diffusion, and surface restructuring. Even as its coma thins, the object remains a valuable probe of how volatile, rich interstellar nuclei respond to long-duration heating, cooling cycles imposed by stellar encounters. The thermal gradients accumulated during perihelion are now diffusing inward, potentially activating volatiles previously insulated from direct irradiation. This delayed sublimation phase is of particular interest because its rate and composition offer indirect metrics of the nucleus's thermal diffusivity and porosity. High porosity, a hallmark of lightly aggregated cometary materials, would facilitate rapid thermal equilibration, whereas a more lithified interior consistent with Atlas's resilience under plasma impact would support prolonged thermal disequilibrium. If the post-perihelion spectra reveal late-release CO2 or cyanogen bands, researchers may infer the presence of stratified volatile layers separated by low conductivity matrices, indicative of a formation environment where materials accumulated in discrete thermal or compositional episodes. Such layering aligns with radial transport models in protoplanetary disks, where solid gas decoupling produces sharp compositional gradients across snowline boundaries. Simultaneously, the dust tail's evolving morphology tracks the gradual decoupling of dust dynamics from gas-driven forces. In comets with diminishing activity, dust trajectories increasingly reflect solar radiation pressure and the interplanetary magnetic field rather than gas drag. Atlas's dust environment will thus transition from complex jet-influenced structures to smoother, more diffuse streams. But because Atlas exhibited anomalous dust behavior earlier, such as the rotating anti-tail scientists anticipate that its debris field may retain subtle imprints of its asymmetric early outgassing phase. These imprints may manifest as bifurcated filaments, variable particle size distributions along the tail's axis, or substructures that preserve the vector history of jets no longer active. Studying these relic structures enables reconstruction of the object's past activity without requiring direct imaging of the nucleus. Moreover, dust polarization measurements taken at increasing heliocentric distances can reveal changes in grain surface roughness and composition, offering clues about the internal materials now being exposed. Dust grains released later in the comet's outbound journey may derive from deeper layers more pristine and less affected by solar radiation processing, thus providing an opportunity to analyze unweathered exosolar dust. On the dynamical side, Atlas's motion through the solar system continues to refine gravitational modelling of hyperbolic objects. Because its trajectory is well constrained by high-precision astrometry, any deviations from predicted paths allow researchers to test the limits of non-gravitational acceleration models, especially those involving CO2-driven jets. Should its outbound trajectory reveal subtle radial accelerations, these could indicate ongoing sublimation from shaded hemispheres, slowly warming from internal heat redistribution. Conversely, an absence of perceivable non-gravitational forces would mark the cessation of significant activity, allowing Atlas's orbit to function as a near-ideal test particle for studying gravitational perturbations from Jupiter-Saturn and the cumulative influences of smaller planetary bodies. Mapping these perturbations with precision improves the ability to reverse integrate Atlas's inbound vector setting, tighter statistical bounds on its possible stellar origin. Though dynamical diffusion across billions of years prevents identification of a specific source star, such reconstructions can exclude categories of stellar environments, for instance high-velocity halo stars, and instead favour formation in dynamically cold disk populations. This narrows the chemical expectations for future interstellar comets and contributes to the broader field of galactic chemical cartography. Another aspect gaining attention concerns the role of cosmic rays in modifying Atlas's nucleus during its interstellar residence. For billions of years, its surface would have been exposed to a constant flux of high-energy particles, inducing radiolytic chemistry capable of transforming simple ices into complex organics, polymerized carbon networks, and refractory crusts. The detection of cyanogen and other carbon-nitrogen species near 3,4 ETU hints at such radiogenic pathways which could create chemical signatures that persist across stellar systems. As Atlas cools, its outgassing rates decrease, potentially allowing high-resolution infrared observations to isolate weaker organic spectral lines, normally masked by more intense sublimation features. Should these faint organics be detected, they would offer a window into pre-solar chemical evolution, an environment unshaped by the sun's radiation spectrum, or early solar system turbulence. This possibility situates Atlas in the context of panspermia-related research, not by suggesting biological material, but by demonstrating how interstellar bodies act as carriers of complex organic chemistry between stellar nurseries. Meanwhile, the broader heliophysical environment continues to influence the object even as it retreats. Though the solar wind density diminishes with distance charge exchange interactions and ion pickup processes remain relevant, especially for objects with diminishing neutral gas emissions. Atlas's fading coma becomes a natural testbed for studying the plasma-neutral transition region, where ionization rates shape the morphology of the residual ion tail. Spectral observations of ion species such as CO2+ or CN+, can reveal how efficiently interstellar cometary gases are ionized under varying solar wind conditions. These observations advance understanding of space plasma processes and illuminate how small body atmospheres behave near the edge of solar influence, a domain rarely accessible with solar system comets, which typically lose detectability earlier in their outbound trajectories. The conceptual importance of Atlas grows as well. Its journey underscores the realization that the galaxy is a dynamic exchange medium for solid bodies, fragments of chemical history migrating between star systems, integrating into new stellar environments, and occasionally offering glimpses into epochs otherwise inaccessible. Atlas thus serves not merely as a comet, but as a chronicle, a physical record of disk chemistry, interstellar exposure, and solar heating dynamics, converging into one measurable object. The theories it inspires, whether concerning mineral inclusions, volatile stratification, or interstellar survivability, are less about explaining a single anomalous visitor and more about constructing a flexible framework that can absorb the diversity of future detections. As astronomical instrumentation improves the questions posed by Atlas, will guide the interpretation of every new interstellar body, which chemical irregularities reflect birthplace, and which reflect evolutionary history. How does long-term exposure to cosmic radiation sculpt volatile inventories? How do stellar encounters alter structural or rotational properties over galactic timescales? These questions form the nucleus of an emerging discipline that blurs the distinctions between planetary science, astrochemistry, and galactic dynamics. In this sense, Atlas's gradual disappearance is not a loss, but a transition. Its physical presence fades, but its scientific influence broadens, dispersing into models, comparative analysis, and new observational strategies. The trajectory it carves through the solar system becomes a conceptual trajectory through the landscape of astronomical thought, a reminder that even transient visitors can redefine the boundaries of inquiry. Its outbound path marks the beginning of a long interpretive journey, one that future scientists will continue as new interstellar emissaries cross the Sun's domain, each carrying their own chemical memories and structural enigmas across the vast interconnected medium of the galaxy. As 3i Atlas recedes toward the dim perimeter of the heliosphere, its gradual transition from active sublimator to cooling interstellar relic illuminates physical processes that could not be observed during its earlier, more energetic phases. With decreasing solar irradiance, the dominant driver of gas release shifts from direct surface heating to the delayed diffusion of volatiles from thermally lagged interior regions. These late-stage emissions, faint and transient, behave like seismic murmurs of a cooling planetary fragment, subtle sporadic pulses that trace the distribution of internal microfractures, pore networks and residual thermal gradients. Their detection provides a rare empirical window into the internal transport properties of an exosolar nucleus, properties that no spacecraft has ever directly measured. If Atlas exhibits intermittent CO or CN release at distances where such sublimation should have ceased, it would suggest the presence of deep cryogenically insulated pockets of volatile ices insulated by refractory layers that restrict thermal conduction. Such a configuration would align with theoretical models of planetesimal accretion in low luminosity stellar systems where weaker radiation promotes the accumulation of stratified, mechanically robust ice dust composites capable of surviving for billions of years in interstellar space. Even as activity wanes, Atlas continues to generate scientific value in its role as a dynamical test particle. Its outbound trajectory, increasingly dominated by gravitational influences, alone becomes a sensitive probe of both planetary perturbations and the cumulative non-gravitational forces applied earlier in its journey. Any deviation from model predictions, even millisecond-level discrepancies, can constrain the magnitude and direction of residual outgassing, thus refining estimates for the total mass lost during its solar passage, and revealing how symmetric or asymmetric its previously active jets truly were. Such precision astrometry is not merely academic. It improves reverse integration of Atlas's inbound motion, narrowing the region of possible stellar origins within the galactic disk. While identifying a specific parent star remains beyond current dynamical capability, due to long-term diffusion and uncertain interstellar encounters, constraining Atlas to a chemically coherent stellar population. Perhaps metal-rich thin disk systems or CO-dominated outer disk environments would represent a major advance in linking cometary chemistry to galactic context. Meanwhile, the dust environment surrounding Atlas undergoes a transformation of its own. With gas drag no longer shaping particle trajectories, the dust tail disperses into a broad radiation pressure-dominated plume that retains fossil information about earlier activity epochs. Larger grains, minimally influenced by radiation pressure, trace the comet's orbital path like a delayed echo of its perihelion passage, while finer grains disperse into curved filaments, sculpted by the interplay of solar photons and the interplanetary magnetic field. By modelling these filaments backward through time, researchers can infer when and where major dust release events occurred, reconstructing elements of Atlas's activity curve long after direct observations become impossible. polarimetric measurements may reveal increasing alignment of dust grains with the ambient magnetic field as gas density drops, offering insights into grain composition and surface charge states. Parameters that help distinguish whether Atlas's dust originated from amorphous carbon silicate-rich aggregates or radiation-processed organic mantles accumulated during its interstellar voyage. As Atlas fades, attention also shifts to the heliophysical processes acting upon its diminishing coma. Ion tail signatures, though faint, can constrain solar wind charge exchange rates at distances where few comets remain observable. This provides valuable calibration data for heliospheric particle flow models, especially in the transitional zone where neutral gas densities fall below ionization thresholds. If CN+ or CO2+ lines persist longer than expected, this may indicate that Atlas maintains a microscopic but steady stream of neutral molecules sufficient to sustain ion pickup processes far from the Sun, an outcome that would revise current models of how rapidly cometary atmospheres collapse after perihelion. Ultimately, Atlas's slow retreat marks not a decline in scientific relevance, but a conceptual shift in its role. What was once a bright observational target becomes an archival cornerstone, a calibration standard for future interstellar detections. Its chemical irregularity, structural resilience, and dynamical precision collectively challenge the assumption that small bodies across the galaxy resemble the icy aggregates of the solar system. In this sense, Atlas functions less as a singular anomaly and more as a catalyst for expanding planetary science into a genuinely galactic discipline, one where the materials of distant stellar nurseries are not remote abstractions, but measurable fragments passing briefly through the Sun's domain. As it vanishes into the background of deep space, Atlas leaves behind a legacy of questions rather than certainties, urging researchers to accept that diversity, not uniformity, defines the architectures of planetary formation. And so the object recedes, carrying the chemical memory of a star we will never see, even as it reshapes our understanding of the many unseen worlds from which such travellers arise. Traveller. As 3 Atlas fades back into the quiet dark, we are left with the soft echo of what it revealed, a wanderer from another star that absorbed a solar storm and continued on without hesitation, reminding us that the universe is older, stranger, and far more patient than we are. And now observer, as its glow diminishes, the mystery only deepens. Atlas showed us that interstellar space is not empty, but alive with messengers drifting between suns, carrying the chemistry of forgotten nurseries and the resilience of time itself. Standing here on our small world listener, it is humbling to realise how little we truly know, and comforting to feel that curiosity is enough. We are small, yes, but we are witnesses. We are finite yet capable of wondering about infinities. So let the silence around this comet stay with you tonight. Let the unanswered questions feel gentle. Let the cosmos keep its secrets a little while longer. Rest well, traveller. Stay curious. The universe will keep watch.